flow for Java developers look like? You build and package your Java application using the usual tools, such as Maven or Gradle. This would typically be a fat jar that has all the dependencies included. In case of a WAR file, you need to think about how to get all the dependencies, such as Tomcat or whatever your application server is. Kubernetes deploy and manage containers. So first thing you need to do is create a Docker image out of your application. This Docker image will need to be published on a Docker repository such that it can be downloaded to the Kubernetes cluster. This could be Docker Hub, Amazon Elastic Container Registry, or any other registry that you have access to. Most common way of deploying to Kubernetes is to use an application manifest. We will cover details about what does this application manifest look like later. An application will create one or more Kubernetes resources, and so it is also called as resource manifest. This manifest uses Kubernetes API to create Kubernetes resources. Multiple types of Kubernetes resources can be created, and we'll discuss them in detail later. This manifest will define the API version, type of the resource, refer to the Docker image if needed, the number of instances of the container, metadata about the resource, and other information. Now you need a Kubernetes cluster where these resources can be created. We'll discuss different options to create Kubernetes cluster later, but you need access to a Kubernetes cluster where the resources can be created. Either you can create this yourself on your development machine, in your data center, or in the cloud. Depending upon your team, there may be a separate ops team that can create the cluster and give you credentials to access that cluster. Last step is to deploy these Kubernetes resources in the cluster. There are multiple ways to deploy these resources, from CLI to deployment pipelines, and will be covered in detail in this course. But in general, this is the workflow for Java developers. You package Java application, create and publish Docker image, create Kubernetes manifest, have access to a Kubernetes cluster, and deploy the manifest to create the resources. Most of these tasks can be automated as part of your build cycle, so even though the number of steps may seem large, the workflow is pretty straightforward. Typically, Kubernetes cluster will be created once, and rest of the steps would be done multiple times during development deployment cycle. For this course, we will use a simple Java application built using Spring Boot. Now we are using Spring Boot, but you're definitely welcome to choose a framework of your choice. End of the day, you need a Java application that needs to be Kubernetesized. This particular application publishes a REST endpoint that can be invoked at a certain endpoint. Now, this application is available as part of the GitHub repo for the course. It's a Maven-based project, and now we have it open here in IntelliJ. Let's take a look at this application. First thing we do is take a look at the source code. It's a very simple application by design because the focus here is on how to package a Java application as a Docker container and Kubernetesize it, not on the complexity of the Java application. So here is my simple greeting controller. As you can see, this is a very standard Spring Boot application. Here is the endpoint where the application is accessible, and it just returns a simple response called as hello. Let's look at the POM XML next. Now you can see this is a very standard Spring Boot starter application. Here are my dependencies. Here is my Spring Boot Maven plugin that allows me to run the application from Maven itself. And I have a Maven profile here, which we'll talk later in the cycle. Now in this application, you can see there are multiple files over here as well, and we will talk through each one of them as we progress through the course. So the first step for us is now to really go and run the application. I got two terminal windows open here. Let's go to my repo directory, and app is where my application is sitting. I'm just going to give a command, Maven Spring Boot run. Now, as I give the command, if this is the first time I'm giving the command on my machine, then it will download all the Maven dependencies. So it could take a while, but because I've run this command on this machine earlier, it'll run rather quickly. So at this point, it's really building my application, packaging my application, and the application rather started very quickly. So now let's go ahead and access this application and see what response do we get back. So I'm going to say curl HTTP localhost colon 8080 hello. Voila, we get a response hello. This is our simple application here, which just returns a response back hello. And that's all we're going to show in this section. So once again, we built our application, we tested our application, we got a response back called as hello. And throughout the course, we'll see as we are progressing through the course, this is the response that we're expecting. Hello is a simple word, but very valuable for us in this particular course. Creating a Docker image and running a container is an important part of the Kubernetes workflow for Java developers. In this section, we'll learn how a Java application can be packaged as a Docker image and run as a container. Let's start with learning how the basic Docker workflow works. There are three components involved in the Docker workflow: a client host, a server host, and a registry. Let's start with registry. Registry is a stateless, highly scalable server-side application that stores and lets you distribute Docker images. This is typically hosted on the internet, such as Docker Hub or Amazon Elastic Container Registry. It could be hosted inside the firewall as well, such as using JFrog's Artifactory or other similar products. This is where all your Docker images, including application images, are published. Docker Client Host is from where the commands to download an image or run a container are issued. This could be your dev machine during development or CI/CD pipeline that is giving the commands to run the containers. The command is typically issued using Docker CLI, which is also installed on the client host. Finally, there is server host, where the images are downloaded for your use and containers are run. There are multiple server hosts to make the application highly available. Each server host has Docker Engine installed that is listening for commands. Let's look at how the flow looks like. App developer creates a Docker image and publishes it on the registry, my app in our case. Developer gives the command from the client host like docker container run using Docker CLI. CLI then translates this command to a REST request and sends it to the Docker engine on the server host. Docker engine checks if the image is already available on the server host. If the image already exists, then it runs the container. If the image does not exist, then it downloads the image from the pre-configured registry and runs the container. The image is stored on the server for later reuse. If multiple instances of the container for the same image needs to run, then the image is only downloaded once unless a newer version is specified. I also have a course on Docker for Java developers that provides much more details about how you can get started with Docker, but the knowledge provided in this course is enough for you to get going. Now that you understand the basic Docker workflow, let's learn the basic concepts around Docker image and container. We'll learn how a Docker image can be created and a container can be run. Let's start by looking at how we can create a Docker image. Docker image can be built from a text-based file, usually called a Docker file. Docker file is a text document that contains all the commands a user could call on the command line to assemble the image. Docker runs instructions in a Docker file in the specified order. A Docker file must start with a from instruction. The from instruction specifies the base image from which you are building. The base image could be an operating system or another general purpose image built by somebody and already has some of the tools that you need for the application. For example, OpenJDK is an image that we will use in our course. Docker file syntax allows multiple instructions. Add is one such instruction that copies new files, directories, or remote file URLs from a source and adds them to file system of the image at the destination path. Another important instruction is CMD that provide defaults for executing container. If there are multiple CMD instructions, then only the last CMD will take effect. This is where typically you will start or deploy your application. Complete set of Docker file instructions are available on docs.docker.com. Here is a sample Docker file that uses Debian operating system, as indicated by the from statement, as the base image, and echoes hello world when the container is run, And as you can see, this is done in the cmd command. Another image relevant to this course is using OpenJDK as the base image this time and prints the version of Java. As a developer, you can start with an operating system base image and add your specific version of the JDK. But if an image with the JDK version that you need already exists, then you're more likely to use that. Docker enables multi-stage builds using Dockerfile. This is enabled by having multiple from statements. Each from statement can use a different base, and each of them begins a new stage of the build. You can selectively copy artifacts from one stage to another, leaving behind everything you don't want in the final image. This allows build and run of the application from the same Docker file and yet have a lean Docker image for production. For example, first stage of a Docker file can be used for development and would typically contain everything needed to build your application. The last stage could be a slimmed down version to use only for production, which only contains your application and exactly what was needed to run it. Specifically in case of Java, as shown in this Docker file, you can use Apache Maven as the base image for development stage and OpenJDK for the production stage. We'll see a live sample of this later in the course. As a Java developer, you often wonder about which Java base image should I be using. OpenJDK Docker image is created and maintained by the community. It is a very popular download and supports a wide variety of tags. If you're looking for a no-cost long-term support downstream distribution of OpenJDK, then Amazon Corretto is one of your choice. An official Docker image for Amazon Corretto is also available at hub.docker.com. So you can easily replace OpenJDK with Amazon Corretto as shown in this slide. Amazon Corretto is meant to be a drop-in replacement for OpenJDK compatible JDKs. You can of course use Amazon Corretto on desktop, on-prem, and in the cloud as a standalone download. It is important to understand what is build context when building a Docker image. Docker image is built using Docker image build command. This command takes a path or a URL. By default, Dockerfile exists at the root of this path or URL. An instruction in the Docker file such as add will resolve files in the local file system using this build context. The build context is sent to the Docker engine, so it is recommended to create a new directory, copy the Docker file and other necessary artifacts in that directory, and then issue the build command. Alternatively, you can also use .dockerignore, very much like .gitignore, to exclude files and directories from the build context. Each image is uniquely identified with a name and a tag. When building an image, you need to assign a name to the image and optionally tag it. If no tag is provided, then the latest tag is used. Here is a sample command that shows how to build an image and give it a name and a tag. Docker image build is the command. -t is an option that allows to specify name and tag in the format name::tag. And dot, in this case, which is current directory, provides the build context. Running an image launches a container. Docker container run command is used to run the container. You just need to specify the image name. As explained in the Docker workflow, the CLI will give this command to the Docker engine, which will check if the image is already available on server host, download it if needed, and then run the container. By default, the container runs in foreground. -d option allows to run the container in detached or background mode. Multiple options to the command can be combined, such as -it. Here, -i keeps stdin open and -t allocates a sudo tty. By default, no ports of the containers are published to the outside world. However, a port can be explicitly made available using port forwarding. This is done using the -p option during the Docker container run command. This allows to map a container port to a specific port on the host. Multiple ports can be published using -p. We learned about the basic concepts of Docker image, how an image can be built, what is a build context. Now let's apply those concepts and actually build a Docker image for our Java application. As explained earlier, we're going to use Dockerfile to build our application. Here, this is a Dockerfile part of our Maven repo. This is the second file that we're explaining here now. As you can see, this is a multi-stage Docker file. Here is my first from statement, and here is my second from statement. The first from statement is using Maven as a base image, and I'm specifying a tag. That means I want Maven version 3.5 and JDK 8. You can look at Docker Hub and see where these images are available and what other tags are available if you need a different version of Maven. I'm giving this stage a name called as build. The first step here is taking a repository.tar.gz, which we will generate in a second, and copying it to a specific directory in the Maven image itself. This directory is existing in the Maven base image. Then we take our application code and copy it to the base image as well in the user source app directory. We set that as a work directory and then give the command called as Maven, where we are referring to the settings for Maven and package the application. Now this really leverages the Maven repository that we will generate locally and repurpose that for creating your application package. At this point, yes, we are using Dockerfile, but is using basic Maven commands to package your Java application. Now comes stage 2, because of the second from statement. In this case, we are using OpenJDK as the base image, and we are using 8JRE as a tag. We don't need the entire JDK or Maven or class files, none of that for our production image. So we take OpenJDK JRE as a base image. We expose the ports from the application. 8080 is where our application is running. 5005 is our debug port, and we'll look at that a little bit later. Then the first command is from the build stage, I'm just copying the target directory into a specific directory here. And that OPT target directory is now set up as a work directory. Now remember, everything that is generated in my first stage is left behind, and only the relevant artifacts are copied from first stage, my development stage, to my production stage. I set up certain Java options here. This will be used when we are debugging our application later. And finally, I fire up my application using java-jar and greeting.var because this greeting.var exists in OPT target directory. Now, let's go to our terminal and create our local repo and run the Docker file to build the image. First of all, we'll go to our GitHub repo and copy the command that we need to run to generate a local version of the repo. So I'm going to copy this command here, go to my terminal, and paste this command. This command is going to download a Maven repository, all the dependencies, and package them locally into one file. Depending upon the speed of your connection, this could take a while, so we're going to speed that up. So now, in my app directory, I have a repository folder. This is my entire Maven repository that needs to be packaged into the base image itself. Let's go back to our browser and copy another command. I'm going to tar this repository so that it can be easily copied into my Maven base image. So let's give this command, and that's going to create a repository.tar.gz for me. If you recall from the Docker file, this is the file that is actually being copied into my Maven base image. The next thing is to really run the Docker file and create my Docker image now. So let's go back to our browser and copy the command again. The command here is docker image build. I'm building the Docker image using -t. I'm giving it a specific tag, and .t being my app directory is my build context. So let's give this command. Now, because the Maven repository is already packaged into your Docker file, it'll take a lot less time to build the image, but it still needs to download all the base images such as Maven, OpenJDK, and so on and so forth. And this could again take a while based upon your internet connectivity. So we'll just speed it up. And our image has been generated now. Let's take a look at the list of Docker images that exist on our local machine now. Of course, we have Arun Gupta /greeting, which was generated about 10 seconds ago. In addition, we also have OpenJDK and Maven as the base images that were downloaded. And there is none image, essentially. That is an intermediate image that was created by Docker itself. But the key part is we generated our Arun Gupta /greeting image 10 seconds ago. The total size is about 500 megabytes, but all the build and the production images are done using a single Docker file using a multi-stage Docker file so you don't have to download any additional tools on your local machine. Now that the image has been built, we're going to launch a container using that image. Let's copy the command here, and we'll go to our terminal and paste this command over there. Docker container run is the command that tells Docker Engine to run the container. -p is an option that maps a container port to a specific port on the host. And Arun Gupta /greeting is, of course, our image name. So let's run this command. And now our Java application that we built earlier, that we ran earlier using Maven, is showing a similar log, but run as a Docker image. I can go to my other terminal here, and I can give the command to access the application again, and I get the same response back. Now, the cool thing here is we are getting the exact same output, but this time from the Docker container that we just launched, built out of the image from our Java application. Let's take a look at what containers are running on our machine. And I can make the window bigger here to give you a better output. So now you can see there is Arun Gupta /greeting image is being used. Here is my container ID. Here is the command that was used to run the container, and it was started about a minute ago. And then you can also see in terms of the ports, I have port 5005, which is not being exposed at this point of time. I'm only exposing port 8080 on the container to 8080 on the host. And that's how we were able to access the application. Okay, so we're going to copy this container ID, and we can stop the container using this ID. And you can see the container has been stopped in my other window here. Now, if I take a look at the list of containers, the container is not running anymore. I can also say Docker container ls-a. It says container is not running. It's a dead container, but we need to remove it. So the next step is Docker container rm, same container ID, and remove the container. And now when I say Docker container ls all, the container no longer exists as well. Let's take a look at a different variation of this command now. We're going to give the exact same command, but this time we're going to run the container in a detached mode using -d switch, or in the background mode. Now you can see the console returned back to us, and it gave us a long container ID. We can copy this container ID here, and we can say Docker container logs and give the command here to see the exact same logs which were displayed earlier to us in the console. Let's access our application again here. I'm going to copy this command that we used earlier, access the application, and get the exact same response back. Once again, the container is running now in a detached mode, but we're getting the exact same response back from our Java application running as a container over there. Now in this case, we can terminate the container. Let's take a look at our container listing again. Here is my container ID. The one that we used earlier was a longer container ID. There's a shorter container ID as well. Let's copy it. And now I can easily terminate the container and remove the container in one command. Docker container rm-f, and give the container ID. And in one command, I have stopped and removed the container. Dockerfile is a common way to package your Java applications as a Docker image. But as a Java developer, you're building applications using Maven, Gradle, and similar tools. How does this building of Docker image fits into your workflow? Jib is a tool that supports that. This section will explain how to build your Docker image using Jib. Jib builds optimized Docker and OCI images for your Java applications. It is commonly referred to as a compiler for containers. Jib allows you to deploy changes fast. It separates your application into multiple layers, splitting dependencies from classes. Now you don't have to wait for Docker to rebuild your entire Java application. Just deploy the layers that changed. A Docker daemon is not needed to build the image. An image is built directly to the registry. Optionally, it can also be built to a Docker daemon. Writing a Docker file to create Docker image for your Java application means you need to learn two different sets of tools, one for Java, one for Docker. You also need to learn best practices around Dockerfile and need to ensure they are consistently followed across the team. With Jib, there is no need to write a Dockerfile. It uses an opinionated base image that can also be run in debug mode. You certainly have the option to choose a different base image. And the most important part is available as plugins for Maven and Gradle and as a Java library. You can also push to any registry of your choice. This allows you to seamlessly integrate this as part of your build process. No need to write Dockerfile or Docker build and push. Jib is an open source tool, and you can get all the details about the tool at its GitHub repo. Now, let's go to IntelliJ, take a look at our POM XML, and see how we're going to integrate this as part of our developer workflow. This is our app. Let's look at pom.xml. And here we are in the Maven pom.xml. And we are looking at the Maven profile. This profile is called as Jib. Here is the group ID, artifact ID, and the Jib plugin version. Make sure you use the latest plugin version because it always has more features into it. Now, in terms of our image, we're using OpenJDK 8JRE as the base image. As we said, the base image can be overridden. Here is the image that we're going to create. Here are my container options. Here are my runtime options, the ports that I'm exposing. Here is an additional option that I'm specifying, which makes sure that the timestamp on my Docker image is always current. Now I'm binding the Docker build goal to the package phase of the Jib profile. What that means is when I give a Maven package command, it will also invoke the Docker build goal of the Jib plugin. Let's see this in action. I'm in the app directory here, and I can give the command Maven package and just the Jib profile. And once I give this command, now if you're giving this command for the very first time, it'll of course download all the dependencies and everything for you, but we have already run the command on this machine, so the dependencies are pre-downloaded. So the cool thing here is you can see is actually building to the Docker daemon, but in between it also tries to retrieve the registry credentials. So something important is how do you configure the registry for your Jib profile? Here is a link on the Jib GitHub repo which talks about how do you use Maven settings. So in your Maven settings, you can set up these values. The registry name in this case is registry.hub.docker.com. Then of course you give your username and your registry password. And that's how it authenticates with the registry. Once you have done that, then you can just give the command. And in this case, it has built the Docker image to our local Docker daemon. So let's look at what our image looks like now. So if I say Docker image ls, this Arun Gupta /greeting image was built just about a minute ago. Let's look at the history of this image. The cool thing about Jib is, as we discussed earlier, it actually splits your classes, resources, and dependencies into each individual Docker layer. It's truly leveraging the Docker layering mechanism in an image and allowing you to iterate more rapidly. This way, the Docker does not have to build the entire application. If your resources and dependencies have not changed, which is typically the case, then only your classes layer is rebuilt and can be easily pushed to the registry. This is particularly relevant in a microservices world because you want that agility for your application and be able to deploy your application a lot rapidly as well. Now, you can, of course, build without the Docker daemon and directly to a registry. So what we can do is we can just say Maven jib:/build, and we can still use the same profile. And now in this case, it's going to build the exact same image, but it's going to push it directly to the Docker registry. It just retrieved the registry credentials and built and pushed the image as Arun Gupta /greeting. We noticed that our Docker image was 489 megabytes, and that is even when we use OpenJDK 8 JRE as the base image, because it contains a lot of JDK functionality that is not needed by our application. JDK 9 introduced module systems that allows you to selectively include the functionality needed for your application and leave everything else behind. We'll look at how the Docker image size for our Java application can be reduced using the tools provided by JDK 9 onwards. Now, JLink is a tool that we're going to use, and that is available in JDK 9 onwards, and it allows to assemble and optimize a set of modules and their dependencies into a custom runtime image or a custom JRE for your application. Now, for that, we're going to use a setup here, and let's walk through that setup a bit. What we have done is we have created an Ubuntu instance on EC2. We have logged into the instance. We have installed the default JDK. When we look at the default JDK version, it is JDK 10, which is beyond JDK 9, and so that works for us. Of course, we have cloned the repo, built the application, installed Docker in there, and built the Docker image so that we can compare the two Docker image sizes. So that's kind of cool. With that setup, let's go to our terminal where our EC2 instance is already logged into. So here we are. I'm going to type java-version, and that is indeed OpenJDK version 10. Now, JLink tool operates on jar files, and our application generated a war file. So we're going to copy the war file to the jar file, and the command for that is in our GitHub repo. Let's copy the first command here and drop it in this directory. So my greeting var is copied to greeting jar. Let's copy the JLink command and drop it here. Once I give this command, JLink is saying create a new directory by the name myjre, add the modules, and in turn is also using a tool jdeps, which says, okay, give me all the dependencies for a particular jar file. So it's saying print module dependencies for greeting.jar. And in addition, these are all the modules that are needed for Spring Boot. So essentially, you are creating a collective list of modules needed for your application and its dependencies. So if we look at our directory here, I have a myjre directory created for us because that's exactly where my custom runtime is available. Okay. So the next thing that we're going to do is look at our dockerfile.jre here. If I look at this, first of all, it's using Debian 9 Slim as my base image because I have a custom JRE, everything baked in. I don't need to go anything fancy. I'm copying my target greeting var, copying my custom JRE, usual ports, set up the root directory, and then fire up the Java or the JVM, this time from my custom directory. And then it goes to greeting.var, of course. Okay, let's go ahead and then build the image. Let's copy the command for that. All we're saying is sudo docker image build to build the image. We're using a specific file, dockerfile.jre. Remember, the default Docker file name is dockerfile. Here is my tag and then my context. So let's build the Docker image. And now if we look at what Docker images do we have locally here, you can see the size difference is significant. As opposed to 489 megabytes that we were getting earlier, now we're getting a 160 megabyte image. So that is pretty cool, actually. So now let's use this image and launch our container. Copy the command for that. In our terminal, let's drop the command. And our container is running. It's running in a detached mode, forwarding to 8080 on the local host, to 8080 on the container. Let's try to access our application now. And we get the same response back. So that is pretty cool. So in this section, we looked at how we can create a custom JRE for your application, package it up as a Docker image, and then access a response back from it. So same Java application, but now using custom JRE in a Docker image. We learn about the purpose of orchestration and how Kubernetes is one of the open source solutions that fits there. Let's learn more about it in a bit more detail. First of all, Kubernetes is an ancient Greek word for helmsman, the person who steers the ship. As we explained earlier, Kubernetes is an open source container orchestration project. Typically, our application consists of multiple containers and runs on a cluster of machines. Kubernetes helps with managing the cluster of machines and scheduling containers on these machines. These are the two primary requirements amongst many others. Because it's open source, it can run on your desktop, in the cloud, or on-prem. Kubernetes is a CNCF project. CNCF is a Cloud Native Computing Foundation, is a vendor-neutral body that defines how cloud-native applications can be built. Kubernetes is one of the projects there, and there are many other projects such as Prometheus, Envoy, and Containerd. The project is one of the most active open source projects by the number of stars, forks, commits, and contributors. It is of course available at github.com/kubernetes/kubernetes. To work with Kubernetes, you use Kubernetes API objects to describe your cluster's desired state, what applications or other workloads you want to run, what container images they use, the number of replicas, what network and disk resources you want to make available, and more. You set your desired state by creating objects using the Kubernetes API, typically via the command line interface kubectl or kubecontrol. These API objects are also called as Kubernetes resources. Typically, a resource manifest file providing complete description of the object will be passed to the CLI. The CLI will then read the manifest and issue the command to the cluster to create or update these resources. You can also use the Kubernetes API directly to interact with the cluster and set or modify the desired state. Once you have set your desired state, Kubernetes works to make the cluster's current state match the desired state. To do so, Kubernetes performs a variety of tasks automatically, such as starting or restarting containers, scaling the number of replicas of a given application, and more. We'll discuss how Kubernetes achieves this later in the course. Kubernetes provides basic monitoring, logging, and health checking for your containers. So if any of the containers are not meeting the health requirements, then they're automatically bounced. Kubernetes also provides a rich ecosystem of tools, and that's what makes Kubernetes that much more a compelling option. Let's look at some of the Kubernetes resources that we're going to learn about in this course. A pod is the basic building block of Kubernetes, the smallest and simplest unit in the Kubernetes object model that you create or deploy. A pod might consist of either a single container or a small number of containers that are tightly coupled and that share resources. Containers in the pod can communicate to each other using localhost and share the file system as well. These containers form a single cohesive unit of service. For example, a web server serving files with a separate sidecar container refreshing the cache. The one container per pod model is the most common Kubernetes use case. In this case, you can think of a pod as a wrapper around a single container, and Kubernetes manages the pod rather than the containers directly. Here is how a sample Kubernetes pod manifest might look like. Let's walk through this. All Kubernetes resources must have API version and kind fields. API version is a string that identifies the version of the schema the object should have, v1 in our case. Kind is a string that identifies the schema this object should have, or the Kubernetes object type, pod in our case. Metadata is a required field for all Kubernetes objects. The only mandatory field in that is name. This field allows a path to be uniquely identified amongst others. You can also specify namespace and UID. Labels is a map of string keys and values that can be used to organize and categorize objects. In our case, app:greeting is a label attached to this pod. Spec stands for specification and defines the desired state of an object. Containers define the list of containers belonging to the pod. This is a static list and cannot be updated at runtime. We will use two fields in our case. Name gives a unique name to a container in the pod. Image is the name of the Docker image. This is the image of our Java application that was built earlier. We learn about the basic building block of Kubernetes resources, a pod. Let's look at some other Kubernetes resources next. A deployment object provides declarative updates for pods. You describe a desired state in a deployment object, and Kubernetes cluster changes the actual state to the desired state at a control rate. Multiple replicas of a pod can be created by specifying the number of replicas. A new version of the pod can be rolled out to all replicas, or you can roll back to a previously deployed version. Here is how a sample Kubernetes deployment manifest might look like. Let's walk through this. You can see the API version is different here. The Kubernetes object to be created here is a deployment, usual metadata section. In spec, replicas is a new entry and defines the number of desired pods. Selector defines a label selector for pods. Match label in that define the exact set of labels that are matched. Any pods matching these labels will be included in the deployment. In our case, it's looking for app:greeting labels. Template describes the pods that will be created. Most of the other entries are similar to pod specification. Ports is a new informational entry here that provides the list of ports to expose from the container. Kubernetes pods are ephemeral, and so an IP address assigned to them cannot be relied upon for the applications to communicate. Kubernetes service provides a logical collection of pods and provides a well-defined API that allows different applications to communicate. It also provides a simple L4 DNS-based load balancing for the pods belonging to the service. The pods are loosely coupled using labels. A service defines the labels that must exist on a pod in order to be included as part of the service. On the other hand, deployment will create pods using those labels. The pods belonging to a service can be dynamically scaled up and down, but the service name continues to provide a stable endpoint for other services to refer. A Kubernetes service can be exposed outside the cluster. This can be done using a cloud provider specific load balancer or a specific IP address. Here is how a sample Kubernetes service manifest might look like. Let's walk through this. Usual API version. Kind indicates this is a service object. Selector defines the labels that must match on the pods to be included in this service. Any traffic to this service is then routed to the included pods. The exact set of labels are specified as key value. Ports provide port information for the service. Port is the port that will be exposed by this service, and target port is a number or a name of the port to access on the pods targeted by the service. A number is mentioned in this case. Let's look at some other useful Kubernetes resources. A daemon set ensures that all or some nodes in the cluster run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, those pods are garbage collected. Deleting a daemon set will clean up the pods it created. A job creates one or more pods and ensures that a specified number of them successfully terminate. As pods successfully complete, the job tracks the successful completions. When a specified number of successful completions is reached, the job itself is complete. Deleting a job will clean up the pods it created. A cron job creates jobs on a time-based schedule. One cron job object is like one line of a cron tab file. It runs a job periodically on a given schedule written in cron format. Stateful set is a workload API object used to manage stateful applications. It provides guarantees about the ordering and uniqueness of those pods. For example, this is useful for running database workloads in containers. There are many other resources in Kubernetes that can be seen on kubernetes.io. As an application developer, typically you'll be working with Kubernetes APIs, but learning how a Kubernetes cluster works is useful too. This section will explain the core concepts of a Kubernetes cluster. This is a slide from a previous section where we explained the generic concept of a container orchestrator. This can be further simplified as shown. The components on the top are collectively called as control plane, and the components on the bottom together can be called data plane. At this level, a simplistic view is where data plane runs your containers and applications and is controlled by the control plane. You rarely interact with data plane directly. Let's take a look at more Kubernetes-centric view of this. Let's look at control plane first. Control plane consists of a master node. The Kubernetes master is responsible for maintaining the desired state of your cluster. The master itself refers to a collection of processes managing the cluster state, which we will discuss in a second. Typically, these processes are all run on a single node in the cluster, and this node is also referred to as the master. It is recommended to replicate the master for availability and redundancy. In addition to the Kubernetes masters, you also need to run etcd, the core persistence layer for Kubernetes. etcd is a distributed key value store. This is where the critical data for the cluster is stored. You can optionally collocate the masters and etcd on the same instances, so you only need to run 3 instances instead of 6 to support the control plane. This makes trade-offs in the operational burden when upgrading your cluster, though you have to make sure that you don't lose quorum on etcd or have to reboot instances. This is one of the many complexities you will encounter when standing up your own Kubernetes infrastructure. We'll talk about how this can be simplified later. Let's look at Kubernetes master in more detail. It consists of an API server which services REST operations and provides the front end to the cluster's shared state through which all other components interact. Controller Manager is a daemon that embeds the core control loop shipped with Kubernetes. It watches the shared state of the cluster through the API server and makes changes attempting to move the current state towards the desired state. Some examples of controllers that ship with Kubernetes today are the replication controller, endpoints controller, and namespace controller. Scheduler is a policy-rich and topology-aware function that schedules containers by taking into individual and collective resource requirements, quality of service requirements, hardware, software, policy constraints, affinity and anti-affinity specifications, and so on. The Cloud Controller Manager is a daemon that embeds the cloud-specific control loops shipped with Kubernetes. This allows Kubernetes core to evolve independently of the vendor-specific code. For example, there is an AWS Cloud Controller Manager. Add-ons extend the functionality of Kubernetes and run on top of Kubernetes. One such useful add-on is DNS that provides name resolution for objects deployed in Kubernetes. Let's look at Kubernetes Worker in more detail. Each worker node runs 2 processes. Kubelet is the primary node agent that runs on each node. Kubelet communicates with Kubernetes master and creates pods and ensures that the containers in these pods are running and healthy. Kubeproxy is a network proxy on each node. It provides Kubernetes networking services on each node. The Kubernetes master controls each node. You will rarely interact with nodes directly. Let's take a look at how control plane and data plane work together to deploy your applications. A Kubernetes resource manifest is used to define a Kubernetes resource. kubectl CLI, or kubecontrol CLI as you may call it, is configured to talk to a Kubernetes cluster, which means to the control plane. A kubectl create command is given using this resource manifest. The control plane then uses the internal components as explained earlier to create the resources on the data plane. A typical flow for a Java developer in this case is to repackage the Docker image with the new application logic, update the Kubernetes resource manifest, and redeploy the resource, and keep going on with it. Multiple Kubernetes resources can be easily deployed to a Kubernetes cluster, and we'll discuss those options later in this course. Let's learn about the options on how we can get started with Kubernetes by creating our first Kubernetes cluster. There are multiple ways to get started with Kubernetes. You can run it easily on your desktop, on-premises data center, or in the cloud. There's a wide variety of choices for running in each of the environments as well. This course will cover running Kubernetes on desktop and in the cloud. Minikube runs as a single-node Kubernetes cluster using a Type 2 hypervisor, such as VirtualBox. It is a single-node Kubernetes cluster running inside a virtual machine. If you're building Docker images, you are likely to have Docker for Desktop installed on your local machine. It provides a seamless way to start a Kubernetes cluster. In this case, a single-node Kubernetes server runs locally within your Docker instance, and the version is not configurable. I conducted a Twitter survey to check which tool is popular for desktop development, particularly using Kubernetes on desktop. Docker for Desktop and Minikube are certainly the most common ones. This course will explain both getting started with Minikube and Docker for Desktop, and we will use Docker for Desktop for all development, in this course because of simplicity and seamless integration with Kubernetes. Let's start with Docker for Desktop first. In order to get started with Docker for Desktop, you go to docker.com, look at products, pick a Docker Desktop. Depending upon your operating system, we are on a Mac machine here. Click on Download for Docker for Mac. Scroll down. You can pick a stable or an edge release. In our case, we'll take the edge release so that we get the latest versions of Docker. Once the download is complete, click on it. Now we go ahead and move the Docker install to our applications directory. And we can go to our applications folder and start Docker. Applications, click on the icon here to start Docker. Click on Next here. You need admin access. And now you can see Docker Desktop is starting for you. And on the top here, what you're seeing is the whale icon that is going up and down, indicating that Docker is getting started. And you will see something very similar on your Docker for Windows as well. Now that your Docker daemon is up and running, now you can enter your Docker ID and password and log in. In order to enable Kubernetes using Docker Desktop, click here, go to Preferences, go to Kubernetes, click on Enable Kubernetes, and apply. This will download all the images required to run your Kubernetes and install it in the Docker instance itself. So it's really that simple. It'll take a while for it to download the images and start it, so we'll speed up the process. All right, after waiting for a few minutes, you can see that Kubernetes is now successfully installed. So let's go ahead and close it. Now we're going to go to our terminal and take a look at it, how we can start using it. First thing we look at is, what is our kubecontrol version? So we say kubecontrol version. And this shows the client version and the server version. Client version, of course, is the version of the kubecontrol CLI or kubectl CLI, and server version is the Kubernetes server version for us. The second thing that we try is kubectl config get context. This shows the Kubernetes server configurations that exist on our local machine. And of course, Kubernetes cluster installed in Docker for Desktop is the only cluster that we have available. And so that's the config that is shown over here. The star over here indicates that that is our current context. So any command that we guide from now onwards using kubectl will be guided towards this particular cluster. Now let's look at how many nodes this cluster has. Of course, as we said, Docker for Desktop is a single node Kubernetes cluster, so it shows a single node. So it's fairly straightforward to get started with Docker for Desktop and enable a Kubernetes cluster. And this is going to be the mechanism that we will use in this course. One of the alternative options to get started with Kubernetes on your desktop is to use Minikube. This section will show you how you can get started with Minikube on your desktop. Now, Minikube requires a type 2 hypervisor. So in this case, we're going to use VirtualBox. Provide the admin access, because VirtualBox would need to create VMs on your behalf. Once VirtualBox is installed, the next step is to install Minikube. Now Minikube is installed. One of the things I want to highlight here is, if you look at brew link override Kubernetes CLI, as part of Minikube, it also installed the latest version of Kubernetes CLI, but it did not override it. So that is an explicit decision that you will have to make. If you want to use the latest Kubernetes CLI, then you can explicitly link it as part of brew command itself. But for now, we'll just move on. So our first thing is to start Minikube cluster. So we say Minikube start. This is going to download the ISO that forms the basis for the VirtualBox image, and then it's going to fire up the cluster, and it's going to download the components in the cluster, and finally our Kubernetes cluster will be ready. This could take a little bit longer depending upon your internet speed. All right, after downloading all the components, configuring them, Minikube cluster is now up and running. So the first thing we're going to do is take a look at our context. In this case, it shows two contexts. The first context is Docker for desktop, because this is what we installed in our previous section, and it shows Minikube, which we just installed. Now the star is around Minikube. What that means is Minikube is the current context. So what that means is any kubectl commands that we give now are going to be configured and used against this particular cluster. So let's try kubectl version now. Kubectl version shows client version, which is the kubectl CLI version. In this case, this is 1.10, and the server version, which is the Kubernetes server version, is 1.12, because that is the version of Kubernetes server installed by Minikube. Let's try kubectl get nodes. And once again, it shows that it's a single node Kubernetes cluster running our local machine. Now, one important thing for you to understand is, as part of pursuing in this course, we will be using Docker for desktop. So let's go ahead and change the context to Docker for desktop. So we will say kubectl config use context is the command, which basically explains that this is the context that I want to use. Copy the context name from here, paste it here, and now the context is switched to Docker for desktop. And now if I say kubectl config get context, both the contexts are shown, but Docker for desktop is the one that is our current context. It's important that you switch to this context, because for all our local development, we will be using Docker for desktop for Kubernetes. After the cluster is created, our first thing is to deploy our application. This is the same Java application created using Spring Boot and packaged as a Docker container. Now, if you recall, our image name was arungupta/greeting. And if you also recall, when we deploy a Docker image as a container in the Kubernetes cluster, is deployed using a resource manifest. So let's take a look at what our resource manifest looks like. Now, I'm in the workspace directory. So let's go to manifest standalone directory. And the first thing we're going to look at is our greeting deployment manifest. There is usual API version, kind, metadata. We're creating a single replica of the pod over here. This is my pod template, in that I'm assigning app:greeting as a label to each pod. It's important we understand this label, because when I'm creating my service later on, it's going to rely upon these particular labels being on the pod. Then I go to the pod spec, in that I'm creating a single container. This is my image name, and here are the ports that I'm exposing. Let's look at my greeting service manifest now. Again, very simple here, API version, kind, metadata, and the selector is the key part here. It's saying any pod that has the labels app:greeting are going to be included in the service, and those are the labels that we attach to in our deployment. Of course, I'm exposing the ports here. The target port is 8080, and the port on which the service is going to be exposed is 8080. And I'm also saying type as load balancer. What that means is, if the service is published in a cloud environment, then the cloud-specific load balancer will be used to expose the service. We'll see the behavior when we deploy this in Docker desktop. So let's go ahead and create our deployment first. So the command to create a deployment is kubectl, which is our CLI, create-f pointing to the resource manifest file, and then the resource manifest file. So this creates my deployment greeting. I can look at the status for the deployment, kubectl get deployment. Here's my deployment name, how much desired, how much current, how much up to date, how much available. All these concepts are applicable when you're doing rolling deployments later on as well. Let's look at our pods. It says a single pod is up and running, and the status is running. Let's look at the logs. I'm going to copy the pod name here, paste it here, and here is the log from the Spring Boot application that we created, and that's shown as part of the log. Now, deployment is created, we checked on the pod, we checked on the logs. Next thing is to create the service. Greeting-service.yaml. Same command. And now let's look at our service status. And as we said earlier, greeting service is now created. By assigning a local host as an external IP address when running on a desktop environment, it makes it easy to access our service. So what are we going to do to access our service? Curl HTTP localhost, because this is the external IP assigned to our service. Port is 8080 and our context is hello. Voila, we got a response hello back from our service. Now, the big difference here is this is the exact same Java application packaged as a Docker container, deployed as a Kubernetes deployment, accessed using a Kubernetes service. So as you can see, we are making progress through our developer workflow that we talked about earlier. So let's go ahead and delete the resources because we will look at different options in the subsequent sections. So kubectl, delete, -f. Let's delete the service first. And then similarly, we can delete the deployment as well. And now if I look at service, of course, there is no service. If I look at deployments, there are no deployments. And if I look at pods, of course, there are no pods. We deployed a Kubernetes deployment and a Kubernetes service using two separate manifest files. But more often than not, we would like to deploy them as a single manifest file. Let's see how we can achieve that. I'm in the workspace directory. Let's go to manifest standalone directory, and we will look at greeting.yaml. Now this greeting.yaml has the exact same deployment manifest that we explained earlier. On line 24 is our key message here, where we are doing 3 dashes, basically showing that this is a new resource is starting from here onwards. And then line 25 onwards, of course, is our service. So essentially, you can put as many Kubernetes objects in a single manifest file separated by 3 dashes over here. So let's go ahead and deploy this manifest as one single file. So kubectl create -f, you guessed it right, greeting.yaml, just one file. And as you can see, the message has changed. It's creating deployment and service for us. And let me show you a different command as well. How do we get access to these? So service, deployment, and pods. In one command, you can get access to all of these objects together. And once again, you have your service greeting created, accessible on localhost, deployment, all status looks good, and pod, once again, up and running. So let's go ahead and access our service here. Localhost, and hello. And we get the same response back. So that is really cool. It allows us to combine our multiple Kubernetes resources into a single manifest file. Now, let's also understand how we can delete all of these resources together. Of course, we can say kubectl delete -f greeting.yaml, but we can also say kubectl delete, and I can say deployment/greeting, because that's the name that I gave to the deployment, and similarly service/greeting, because that's the name of my service. This will delete both deployment and service. And once again, if I try to access service, deployment, and pods, none of them is available, at least for my application. Deploying your application to Kubernetes should feel like deploying one single application as opposed to deploying multiple manifest files one at a time. This section will explain what are Helm charts and how they can be used to deploy Kubernetes applications. Kubernetes Helm offers a simple way to package everything into one application and allows to manage multiple releases of it. Helm packages multiple Kubernetes resources into a single logical deployment unit called charts. A Helm chart is simply a collection of YAML template files organized into a specific directory structure. Charts are somewhat analogous to deb and RPM files. However, since they are text-based, charts are versionable and simple to maintain with familiar SCM tools. A single chart might be used to deploy something like, say, our greeting pod, or something more complex like a full web application consisting of multiple microservices. Installation of a Helm chart in the Kubernetes cluster is called a release. A single chart may be installed many times into the same cluster and create many different releases, each with different configuration. For example, you can install 3 versions of an application by running helm install 3 times with a different release name. Helm is a tool that streamlines installing and managing of Kubernetes applications. Think of it like apt, yum, or homebrew for Kubernetes. Let's learn some more Helm terminology. Helm charts may be stored on dedicated HTTP servers called chart repositories, or just repos. A repo is a simple HTTP server that can serve an index.yaml file that describes a batch of charts and provides information on where each chart can be downloaded from. A Helm client can point to 0 or more chart repositories. By default, Helm clients point to the stable official Kubernetes chart repository. Templates are Kubernetes configuration files in a chart that are templatized. Each configuration file goes through a template rendering engine in Helm to generate a corresponding Kubernetes manifest file. These files are then used to create Kubernetes resources in the cluster. Let's look at how a sample chart might look like. This is the directory structure of a Helm chart for our greeting application. Let's look at some of the files. The first one to look at is chart.yaml. This is a YAML file and contains information about the chart. Let's look at individual fields in this file. API version is a required field and defines the chart API version. For now, its value is fixed at v1. Future versions of Helm may update this value. App version is an optional field and defines the version of the app that this contains. Description is an optional single-sentence description of this project. Name is a required field and defines name of the chart. Version is version number of the chart. It must follow the semantic versioning 2 standard. These version numbers are used as release markers. Packages in repositories are identified by name plus version. For example, this chart will be identified as greeting-0.1.0.tgz. Let's look at values.yaml file next. Values.yaml is one of the ways by which predefined values for templates can be specified. These are specified using nested YAML syntax and accessible in the template files using values object. We will see how this object is being used in the next slide. Let's take a look at one of the template files, deployment file for greeting in this case. If you notice, this file is very much like a Kubernetes configuration file, but allows template language to be specified. Values object is used to refer to the values specified in values.yaml. This allows to specify common values such as port numbers and replica counts to be specified at a central location and then used inside Kubernetes configuration file using templates. This promotes don't repeat yourself or dry design pattern, reduces deployment complexity, and also improves developer productivity. Finally, let's take a look at Helm 2 architecture and learn how a chart is converted into a release. This architecture has already evolved for Helm 3, so please refer to the latest documentation for that. Our starting point, either way, is a Kubernetes cluster. Helm has 2 parts, client, which is also called as the Helm client, and server, which is also called as Tiller. Tiller runs inside of your Kubernetes cluster and manages releases of your charts, also the installations of your chart. Helm runs on your laptop, CI/CD, or wherever you want it to run. Charts can be stored on disk or fetched from remote chart repositories like Debian or Red Hat packages. The Helm client and server are written in the Go programming language and use the gRPC protocol suite to interact with each other. Currently, that library uses REST plus JSON. Tiller server stores configuration information about charts using config map in Kubernetes. The client sends the interpolated configs to Tiller. It uses the configuration data and communicates with Kubernetes API server to create a new release of the chart. This explains how charts are deployed as releases in a Kubernetes cluster. At a high level, Helm client manages charts and Helm server manages releases. We have deployed multiple Kubernetes resources using multiple manifest files. We've also deployed multiple Kubernetes resources using a single manifest file. Let's see how we can deploy multiple Kubernetes resources using a single Helm chart. The first command for that is to install the Kubernetes Helm CLI. This command will download the latest Helm CLI and install it on your machine. If you already have a prior version of Helm CLI, then you can of course use brew upgrade Kubernetes Helm, and that will upgrade to the latest version of Helm CLI. Let's see what version of Helm it is. If we see, it says 2.12.1, and that's for the client. On the server side, it says could not find tiller, because so far we have not initialized our cluster or the Kubernetes cluster with Helm. Let's make sure our context is set correctly. So kubectl config get context. As we have been using in this course, Docker for desktop is the right context for us. So now at this point of time, I can just say Helm init. And this will initialize my Kubernetes cluster with tiller. So essentially, it will install tiller as a component in my Kubernetes cluster. Now, how do we verify that? I can say kubectl get pods, and it installs tiller in the kube system namespace. So I can specify the kube system namespace here. And here we can see tiller is running 1 out of 1 and in a running state. So that's good for us. Now we need to deploy our Helm chart as an application to the Kubernetes cluster. We'll go to manifest charts directory. Our charts are all existing in this location. So for now, we're going to look at my app. This is the directory where our Helm chart exists. This is a chart that we explained in the previous section as well. So we're not going to go through the explanation, but we'll go ahead and now deploy our application. So Helm install is the command that we're going to use. Give this application a name, and then we will give the top level directory where my Helm chart is installed. We give this command, and it creates all my resources. So deployment, pod, and service, and everything that we wanted to create over here. Now, with a single command, we have deployed all the resources. Let's see how we can see all of those resources using a single command as well. So we say kubectl get service, deployment, and pod. And it shows that our greeting service is created, so is deployment, and so is pod. Now let me show you a command on how we can access this service very easily. We have been using curl http localhost 8080/hello. This is our usual way to access the application. And as expected, we get the response hello. Now this time our same Java application packaged as a Docker container deployed as a Helm chart in the Kubernetes cluster. Let me show you another command by which you can easily access this. So for that, we're going to go to browser and copy a command. Here is a command that we're going to copy, and we will paste it here. Now, what we're doing here is we're saying curl http, and then in the dollar here, we're saying kubectl get me the service greeting, use the JSON path, and in the JSON path, essentially get me status, load balancer, ingress, and the host name, which is going to be localhost for us. And then I say :8080/hello. And this returns the exact same response to us. Now, the advantage of this particular command is this would work across your different environment, whether it's your cloud, whether it's your desktop, whether it's your on-prem, and this is a universal command that will work all across. So finally, let's go ahead and see how we can delete our application. So in order to delete all the resources, we go to say purge and give the application name. And with one single command, once again, my entire application is now deleted. Now, if I try to look through all the resources once again, of course, none of them exist anymore. As a Java developer, you're always dealing with tools like NetBeans, IntelliJ, and Eclipse. And you're used to debugging your application in those IDEs. Now, how do I bring those skill sets when I'm building my application in Kubernetes and deploying in them? This section will explain how you can debug a Kubernetes pod if the cluster is running on your local machine. So first thing first, deploy our Helm chart. So let's go to our manifest charts directory. And now I'm going to install my Helm chart. Helm install name my app. And this deploys my application. Let's confirm it. We of course need to say get before this. And so we can see all the resources have been successfully deployed. So we are in good shape over there. Now let's go to IntelliJ, for example, in this case, and set up a breakpoint over there. Here is my Maven project that is in IntelliJ here essentially. And here is my greeting controller. This is sort of my main business logic. Remember, this is a very intentionally simple application. So now what I'm going to do is I'm going to just set up a breakpoint over here. That's the first thing I need to do. The second thing I need to do is I need to set up IntelliJ so that it can connect to a remote JVM. So I go to run, debug, edit the configuration here, add a new remote config here, and we're going to call it as Kubernetes and take everything else as default. It says localhost 5005. That's where it's going to connect to our JVM. And it expects that this is the command that's going to be in your Docker image essentially. Now, if you remember from our Docker file on how we built this image, this is exactly the command that we took and inserted into our Docker file as _java_options. So that's sort of the way by which you are connecting your JVM and your Docker file and making sure the options go pass through. And then in the service and in the deployment, we were exposing those ports so that now they're then accessible to the outside world as well. So let's hit on debug here. And IntelliJ is now connected to the target VM and is waiting for somebody to initiate a request on that. Okay. So in our terminal, we're going to access our service and we will say curl http localhost :8080 hello. Let's invoke the service. As soon as we invoke the service, we can see our shift automatically focused to IntelliJ. This is because IntelliJ now received the request that, hey, somebody is talking to me on the remote JVM, and it shows the complete path for you on how the Java call hierarchy looks like. Now, in our case, we of course don't have any variables defined, but if there were, then it'll show you all the class fields. You can essentially use your standard Java debugging tools to talk through this, to walk through this, to trace through this, see all the values, and then debug your Kubernetes application very easily. Now, at this point of time, I can just say, go ahead, run the application. So of course, the application execution finished, but let's go back to our terminal and see what the output is over there. As expected, output is certainly hello. So once again, now we saw how we can debug our Java application running as a Kubernetes pod deployed in a local Kubernetes cluster. There are multiple ways to run Kubernetes in the cloud. CNCF survey shows that over 50% of Kubernetes runs in the AWS cloud. This section will introduce Amazon Elastic Container Service for Kubernetes, or EKS, or Amazon's Managed Kubernetes Service. Amazon Elastic Container Service for Kubernetes, Amazon EKS, makes it easy to deploy, manage, and scale containerized applications using Kubernetes on AWS. Amazon EKS runs the Kubernetes management infrastructure across multiple AWS availability zones, automatically detects and replaces unhealthy control plane nodes, and provides on-demand upgrades and patching. You simply provision worker nodes and connect them to the provided Amazon EKS endpoint. Secure and encrypted communication channels are automatically set up between your worker nodes and the managed control plane, making your infrastructure running on Amazon EKS secure by default. Amazon EKS is certified Kubernetes conformant, so you can use existing tooling and plugins from partners and the Kubernetes community. Applications running on any standard Kubernetes environment are fully compatible and can be easily migrated to Amazon EKS. AWS actively works with the Kubernetes community, including making contributions to the Kubernetes codebase that help Amazon EKS users take advantage of AWS services and features. Let's take a look at the user experience to create an EKS cluster. First, you need to provision an EKS cluster. This can be done using AWS Console, AWS CLI, CloudFormation, or Terraform templates, or other third-party tools. This creates a highly available and secure Kubernetes control plane spread across multiple availability zones. You don't need to think about your master configuration. This also includes things that give you sweats at the night. Is etcd being monitored, encrypted, and backed up? Is your security group configuration is right for your masters? Did we deploy this in a way that is in accordance with best practices on AWS? The control plane runs in Amazon's account. Second, you need to deploy the worker nodes for your EKS cluster. This creates the Kubernetes data plane and where the application is deployed. Data plane runs in the user's AWS account. This means that you control the instance type, the configuration, the army used, the network configuration in your VPC, security groups, access control lists, and everything else. You can use spot instances or reserved instances. They are your instances. Finally, you need to connect the data plane and the control plane. This creates the complete EKS cluster. This entire workflow of creating control plane, creating data plane, and connecting the two together is offered as a seamless experience by third-party tools. One such tool available in the open source is EKS Cuddle. This tool is created by Weaveworks and will be used later in this course. Now, you can deploy your applications to this Kubernetes cluster. In AWS, identity and access management defines how AWS resources can be accessed securely. Because Amazon is hosting Kubernetes as a service, there is a need to provide authentication on the API endpoint with IAM. Let's dig into how this works. AWS IAM Authenticator is an open source project in SIG AWS in the Kubernetes community and helps with passing AWS identity. So when a kubectl call is made, let's say get pods, IAM identity is passed along with the Kubernetes call. On the backend, Kubernetes verifies the IAM identity with AWS auth service. This is purely authentication. The authentication response is then sent back to Kubernetes, and Kubernetes checks its internal RBAC mapping for the authorization. This determines if my original get pods call was allowed or denied. Finally, Kubernetes approves or denies the request. Let's talk a little bit more about some other highlights of Amazon EKS. Amazon EKS makes it easy to update running clusters to the latest Kubernetes version without needing to manage the update process. Kubernetes version updates are done in place, removing the need to create new clusters or migrate applications to a new cluster. EKS gives you flexibility and control over what instances you can run. Because of this flexibility, for example, it's super easy to get started with machine learning workloads on EKS. To support this, we have a dedicated GPU army that makes it easy to run CUDA framework workloads on P2 and P3 instances. This is in the AWS Marketplace. You click subscribe, and you can check these nodes into your cluster and go build your next Skynet on EKS. EKS also gives you flexibility over the operating system you can bring. If you want a pre-made army, we have the EKS Optimized Army based on Amazon Linux 2, and Canonical builds an EKS army as well. We also provide Packer scripts on how these armies are created. This allows you to create custom armies matching your corporate requirement. Amazon EKS is available in a large number of AWS regions today, and this list is constantly growing. Regional Product Services table provide an accurate and up-to-date list of regions where EKS cluster can be created. As discussed earlier, there are multiple ways to get started by creating an Amazon EKS cluster. We are on the Amazon EKS website. You can certainly click on Start using Amazon EKS, and there is a lovely getting started guide that you can follow along to create an EKS cluster. EKS Cuddle, as we discussed earlier, is a third-party tool created in the open source by Amazon's partner, Weaveworks, and this tool can be used to create a EKS cluster. It provides a seamless experience where the control plane, the data plane, and the connection of the data plane to the control plane is all done using a single command. So, in order to get started, let's first install the EKS Cuddle CLI. This command will install the EKS Cuddle CLI. As you can see, it downloaded EKS Cuddle 0.1.17. Make sure you're using the latest version of the EKS Cuddle CLI. It also downloaded the AWS IAM Authenticator. The workflow for this we explained in the previous section. So our next step is really to take a look at what our EKS Cuddle version looks like. The version is indeed 0.1.17. And then now we're ready to create our cluster. So we're going to say EKS Cuddle create cluster. We want to give the cluster a name. In our case, we'll call it as Kate's course. And we want the number of nodes to be 4. By default, it creates a cluster in US West 2 region for AWS, and you can certainly specify a region using -- region switch over here, or you can say -- help to see the complete list of options that the EKS Cuddle provides. This also uses the underlying AWS CLI on your machine that is pre-configured for your access keys. So let's go ahead and press enter here. All right, after waiting for a few minutes, it creates a control plane, creates a data plane, connects the data plane to the control plane, and our overall Kubernetes cluster is up and running. As in previous cases, first thing we're going to do is take a look at what configurations are available. Now in this case, of course, Docker for desktop and Minikube are from previous sections, and we can see there's a new context that is available to us, which is our cluster that we just created. And also the current context. What that means is any kubectl commands that I give now are going to be directed to this particular cluster. So let's get the number of nodes in this cluster. And because we said 4 nodes, is rightly showing us 4 nodes in the cluster. They've been up for about a minute, status is all ready, and they all have version 1.11.5. That's the version that is supported by Amazon EKS today. We can also say kubectl version and just print the short version. So now it shows the kubectl CLI is 1.10.3 and server version is 1.11.5. Let's also see how the cluster looks like in our AWS console. So here I am in AWS console. I can look for EKS service. Click on this here. Now, my EKS is a cluster that I created earlier, but Kubernetes course is a cluster that I created just now. This screen shows you more details about the cluster. So once again, Kubernetes version, API server endpoint, cluster on, certificate authority, role on. These are all the values that you need to access your cluster. Now that our Kubernetes cluster is running in the AWS cloud, we need to look at how can we migrate our application that was running in the Kubernetes cluster on this desktop to the Kubernetes cluster running in the cloud. That's called as migrating your application from one cluster to another cluster. That's a typical flow that you will go through where you're building your application on your local desktop and we're ready to go production, then you may migrate to the cloud. So first of all, let's look at kubectl config get context. The context is indeed set correctly to the cluster running in the cloud. Now, we deployed our application as a Helm chart, and so we need to deploy Helm in this particular cluster as well. Now, Helm's server-side component Tiller requires special permission on the Kubernetes cluster. We need to build a service account for Tiller to use and enable permissions for it, and then we can install Helm in EKS. So let's look at the commands on how we can do that. Here are the commands by which we can install Helm on EKS. I'm going to copy this command and paste it in my terminal. First of all, it creates a service account. Then it gives the right RBAC permissions, and then it initializes Helm using that particular service account. So here we go. Now our Helm is up and running in our Kubernetes cluster running in the cloud. And how do we verify that once again? We can say kubectl get pods and look in the kube system namespace. There it shows Tiller is up and running. So now we are ready to deploy our application into the Kubernetes cluster. So once again, go to manifest charts directory, and we can just say Helm install name my app, and of course our root directory for the chart, my app, and press enter. This time, the exact same application that was deployed on our local desktop cluster is now getting deployed to the Kubernetes cluster running in the cloud. So essentially, in terms of migration, what you're looking at is literally just change your context from one cluster, which is running on your desktop, to another cluster, which is running in the cloud, and then redeploy the application. The fact that your manifests are exactly the same, the Docker images are exactly the same, so there is very low impedance mismatch in terms of your dev and the prod environment. Oftentimes, I've seen developers building their development cluster even in the cloud, and that's certainly an option. So you can use EKS Scuttle to create multiple clusters, but the mechanism is still the same. You set up a context, you do your development cluster, and when you're ready, change the context to the prod cluster, and then migrate your application. Let's look at our service here. And while we are at it, let's look at service deployment and pods. Now, here is our service up and running. Deployment looking good, and so is pod. Because in this case, service is deployed in the Kubernetes cluster running in the AWS cloud, and with type colon load balancer, ELB or an elastic load balancer is automatically provisioned for you, thereby exposing the service. And of course, the ports are listed over here. So 8080 is a port where this service is going to be accessible, and 5005 is our debug port. Now, it takes about 2 to 3 minutes for the ELB to be provisioned and ready to be used. So we'll speed up the process, and then we will see how we can access this service. After waiting for a couple of minutes, we expect that the ELB would be up and provisioned. So let's go ahead and access the service. For that, we're going to copy the command from the browser. Here's a command that we're going to copy. And if you recall, this is the same command that we have used earlier, and it really allows us to access a service independent of the cloud environment or the desktop environment. Copy and paste the command here. Once again, it's saying curl http kubectl get service greeting and give me the host name for the ingress using the JSON path. Here is the port, and here is our context. Voila. This is our service now running, packaged as a Docker container, running inside a pod in a Kubernetes cluster, running in the AWS cloud, and we are accessing it from our console. This section will introduce what is a service mesh and particularly more about Istio. Service mesh is a dedicated infrastructure layer for handling service-to-service communication. It is responsible for the reliable delivery of requests through complex topology of services that comprise a modern cloud-native application. This is particularly relevant in today's world, where developers are leaning towards microservices-oriented architecture. In the context of Kubernetes, a service provides a simple OSI layer 4 DNS-based load balancing for the pods belonging to the service. Service mesh addresses OSI layer 7 load balancing needs and a lot more. Let's look at them next. Service mesh ensures that a communication between a service A and a service B can be done safely and securely. This could include defending against man-in-the-middle attack using encryption and mutual TLS. This also includes auditing capabilities to check who did what at what time. Reliability ensures there are provisions for health checks, timeouts, deadlines, circuit breakers, and retries. Service mesh provides visibility into your microservices application. It ensures there are top-line metrics like request volume, success rates, and latencies. This also includes monitoring and distributed tracing across different services. Configurability allows to do traffic shaping between different services. This enables capabilities like load balancing, canary and A/B testing, shadowing, and fault injection. You can also do adaptive and zone-aware routing between services using this. Trying to solve these problems with an application or framework of your choice not only makes the application complex, but also difficult to maintain. This becomes further complicated if your application consists of multiple microservices, potentially each written in a different language. The combinatorial explosion of libraries for different languages and platforms makes it extremely difficult to maintain such a solution. A common design pattern is where all logic for how the microservices need to connect, including safety, reliability, observability, and configuration, is configured in a sidecar proxy. This works very well in Kubernetes, as the proxy is installed as a sidecar container right next to the application container in the same pod. Some of the advantages of this approach are: this out-of-process architecture decouples the application code from communication management code. No change is required to the application code to add the capabilities offered by the sidecar. It also decouples application install from application upgrades. And finally, it minimizes inconsistencies across different microservices. All the external communication now happens through this sidecar, and because of being in the same pod, application container and proxy can talk to each other easily. Service mesh can then extract a wealth of signals about traffic behavior and use that to enforce policy decisions such as security. It can also send them to monitoring systems to provide information about monitoring and observability of the application. A microservices-based application has different microservices, each with multiple replicas. Each replica is a pod. For a service mesh-enabled application, each pod has a sidecar container. This fleet of proxies is the service mesh data plane. How do we tell every proxy what to do? How do we ensure the safety, reliability, and configuration can be done for each proxy? How do we get observability across these proxies? We need a control plane. A control plane to manage the service mesh data plane is required. This control plane handles tasks such as creating new instances and injecting the proxy as sidecar, management and monitoring, observability, security between different services, and implementing application-wide policies. Istio provides a control plane for this service mesh data plane. You can find everything about Istio at istio.io. To go with the nautical puns around Kubernetes, Istio is Greek for sail. It uses an extended version of Envoy as a sidecar proxy. Envoy, originally built by Lyft, now a CNCF graduated project, is a high-performance C++ distributed proxy. Envoy is known to run on tens of thousands of nodes and process over 10 million requests per second in the mesh. Istio leverages Envoy's many built-in features, for example, dynamic service discovery, load balancing, TLS termination, circuit breaker, and fault injection. Formal definition of Istio from istio.io is that Istio allows to connect, secure, control, and observe services. This is analogous to the needs of a service mesh that we explained earlier. Let's look at some core features of Istio to wrap up this section. Istio provides the following core features. Istio rules configuration and traffic routing lets you control the flow of traffic and API calls between services. Istio simplifies configuration of service-level properties like circuit breakers, timeouts, and retries, and makes it a breeze to set up important tasks like A/B testing, canary rollouts, and stage rollouts with percentage-based traffic splits. With better visibility into your traffic and out-of-box failure recovery features, you can catch issues before they can cause problems, making calls more reliable and your network more robust. Istio's security capabilities free developers to focus on security at the application level. Istio provides the underlying secure communication channel and manages authentication, authorization, and encryption of service communication at scale. With Istio, service communications are secured by default, letting you enforce policies consistently across these diverse protocols and runtimes, all with little or no application changes. Istio's robust tracing, monitoring, and logging gives you deep insights into your service mesh deployment. Gain a real understanding of how service performance impacts things downstream and upstream with Istio's monitoring feature, while its custom dashboards provide visibility into the performance of all of your services and let you see how that performance is affecting your other processes. Istio is platform independent and designed to run in a variety of environments, including those spanning cloud, on-prem, Kubernetes, services registered with console, and more. The policy enforcement component of Istio can be extended and customized to integrate with existing solutions for access control lists, logging, monitoring, quotas, auditing, and more. Let's install Istio on our Amazon EKS cluster and have some fun with it. In the GitHub repo, there is a link to a blog post that provides complete details about how you can get started with Istio on Amazon EKS. It explains Istio architecture and how you can get started with it. For convenience, we have summarized the command here. The first thing we need to do is download Istio. Copy the command here. In our terminal, I'm in the home directory. Give the command. This is going to download the latest Istio release. Now notice this is Istio 1.0.5. We need to include Istio bin directory in our path, and there is a convenient command for that. So copy it, paste it, and now Istio bin directory is in our path. The only thing remaining to essentially get Istio up and running in our Kubernetes cluster is to install Istio. So let's go to our Istio directory here, and there is a Helm chart that is already available for Istio. So we're going to say Helm install, run this in a synchronous mode, call this deployment Istio, in the namespace Istio system, and the Helm chart by itself is in the directory install Kubernetes Helm Istio. Because we are doing this in a synchronous mode, it will wait for all the images to be downloaded and configured and installed And now Istio is ready to roll. Let's take a look at what pods have been installed as part of this. kubectl get pods, and remember our namespace was Istio system. And so you can see all the pods have also been installed. And this completes our Istio installation on the Amazon EKS cluster. So far, we have deployed a Helm chart to our Kubernetes cluster, which has one Java application. And that Java application returns a response, a simple response, hello. Now, we want to deploy an application to our Kubernetes cluster as two Java applications. One of them returns a response of hello, and the other one returns a response of howdy. And then we're going to have some fun with Istio using those two applications. Now, remember, we talked about Istio works using a sidecar, and particularly in this case is Envoy sidecar proxy. So how do we tell Kubernetes cluster to make sure for every deployment inject a sidecar proxy? Well, there are a couple of ways to do that. The first one is by which we can say for any object that is injected into the default namespace, give it a label called as Istio injection enable. And once you give that label, essentially Istio will make sure there is a sidecar which is injected into each deployment. Let's try that first. Copy. I'm into the workspace directory. Paste. And now my default namespace is labeled with Istio injection equals enable. Now we understand in certain cases you may not have the ability to add any random label to the namespace. It may be a different namespace, in which case you can use Istio cuddle is a CLI that is in Istio download bin directory. And then you can use Istio cuddle kube inject command to point to your manifest, which will generate a new manifest, which will have a sidecar already mentioned into your pod spec. Then you can take that new manifest and kubectl apply it so that now when your manifest is deployed to the Kubernetes cluster, it has not only your application container or any other container that you have specified, but in addition, it also has that sidecar container. Okay. Well, we are using the default namespace injection here. So let's go ahead and deploy our application. Manifest, charts. Let's see what applications are deployed using Helm right now. Well, Istio, of course, we installed that, and my app. Let's delete the my app application first. Helm delete my app and purge it. So that deletes my application. Now I'm going to go to my app, hello howdy. Okay. And if I go to the templates directory, because this is a Helm chart, if you look at the listing here, there is a greeting deployment hello and a greeting deployment howdy. Now these are two separate files with two separate deployments. One of them points to a Docker image, which has a Spring Boot application that returns a response hello, and the other one points to a Spring Boot application that returns a response howdy. Let's look at these two files. So greeting deployment hello and greeting deployment howdy. The first one is greeting hello. The pod spec has labels app::greeting and greeting, and this is the value defined in the values YAML of the Helm chart. And then the usual stuff over here. If I look at greeting deployment howdy, the name is greeting howdy, same replicas, app::greeting, and the howdy tag. And of course, the image here, of course, is using the howdy tag as well. So let's go ahead and install this Helm chart. Make sure we are in the right directory. Then we say Helm install name my app. And in this case, we need to say my app hello howdy. The service is going to get deployed here. One of the things I want to point out here is service also has the type as cluster IP. We don't want the service in this case to be published as an external load balancer. As we will see in the next chapter, we will create a Istio ingress gateway because that's essentially what will help us guide the traffic splitting. So let's look at kubectl get deployments. We got two deployments and they're both looking good. Get pods. There are two pods, two of two. One application container, second is the sidecar container. Both looking good. Now let's look at the two containers that are in the pod. And that I can get by kubectl get pods. I can say, show me all the pods that have the label greeting hello. And now I'm going to use a JSON path here. So call it JSON path here. And in this JSON path, what I'm going to specify is show me all the items that are in there. In the items, give me their part spec. Then pick up all the containers over there and then give me their name. And this is my command. And when I press enter, I get greeting and Istio proxy as my two containers running for greeting hello. Now I can repeat the same command, and this time we can do the same for howdy. And what we'll get is again greeting and Istio proxy, because essentially the containers within the deployment are still called as greeting. So now what we have done is we have deployed the same Java application, but now it has two deployments, one returning hello, one returning howdy. In order for Istio to be able to do its work, we need to create certain Istio resources. Let's first understand what Istio resources we need in our case, and then we will create them next. Destination rule is a resource that allows to specify one or more named sets that represent individual versions of a service. Each version is uniquely identified using the labels attached to the pod. It also defines policies that apply to traffic intended for a service after routing has occurred. These rules specify configuration for load balancing, connection pool size from the sidecar, and outlier detection settings to detect and evict unhealthy hosts from the load balancing pool. Traffic policies can be applied to all sets or overridden at subset level. A virtual service defines a set of traffic routing rules to apply when a host is addressed. For example, what weight should be assigned to multiple services defined in this virtual service? How many times a HTTP request should be retried if the request fails? Another rule could be what HTTP faults can be injected when forwarding requests to the destination service. Actual rules are defined for different protocols. At this time, HTTP, TCP, and TLS are supported protocols. If the traffic is matched by the protocol, then it is sent to a named destination service or subset or version of it that must have been defined by a destination rule. Gateway describes a load balancer operating at the edge of the mesh, receiving incoming or outgoing HTTP/TCP connections. A gateway allows Istio features such as monitoring and routing rules to be applied to traffic entering the cluster. Its specification describes a set of ports that should be exposed, the type of protocol to use, configuration for the load balancer, etc. A virtual service can then be bound to a gateway to control the forwarding of traffic arriving at a particular host or gateway port. Let's look at some code now. Now that we understand what these resources are, let's look at how these resources look like, particularly for our application. Let's go to manifest, standalone directory. I'm going to open up greeting istio.yaml. All the resources that we need for our application are defined in this particular one file. First is, of course, the gateway resource. It's using the default Istio ingress gateway and accepts all hosts. The destination rule is a second resource. It has two subsets, named greeting hello and greeting howdy. And the way they're identified are really by using greeting:hello and greeting:howdy labels. And last, we have our virtual service, which accepts greeting as a gateway. It requires greeting.com to be the host. So essentially, when somebody is making a request, either it should be coming from greeting.com or we should have a host header in the request. And we'll see this when we actually make the request. And here, finally, we have HTTP-based routing, which is pointing to two destinations. One of them is a greeting hello subset. The other one is a greeting howdy subset. And the traffic between them is split 50-50. So let's go ahead and create these resources. In one command, because all the resources are together in the same manifest, we are able to create all the resources. So now let's look at kubectl get virtual service, destination rule, and gateway. All our Istio resources have now been created. Now remember, our service did not have a type as load balancer, And so the service has to be only accessed using the ingress gateway, because that's exactly where Istio traffic splitting and all the Istio rules can be applied. So for that, we need the host and the port where Istio ingress gateway is running. For that, I'm going to go to the browser, copy a command to set up my host and port. Here's the command. Copy it and paste it here. It's looking for service Istio ingress gateway in the Istio system namespace and getting the load balancer ingress hostname and the HTTP to port. Now we just need to access the service and see how our responses look like. Let's copy this command. Let's see what this command is doing. Well, first of all, we are doing this in a for loop. So we are invoking it 10 times. Then we are curling. What are we curling? We are curling HTTP ingress host and port that we just set up. Hello is, of course, our context of the Java application. And we're also sending the HTTP host header, which is required for the ingress gateway to do the traffic splitting. Okay, let's go ahead and invoke it. And rightly, you see 3 hellos, 4 howdies, 1 hello, 2 howdies. Now, you may say, hey, this is 4 hellos and 6 howdies. And our virtual service said that the split has to be 50-50. Now, again, that 50-50 is an approximation. So if you do over a large set, then this would turn out to be 50-50. We saw 2 Java applications deployed as pods in our Kubernetes application. When we were invoking that application, the traffic was about 50% split between each of those applications. But one of the power of Istio is that the rules configuration and traffic routing lets you control the flow of traffic and the API calls between services. It can exactly define how much traffic should go to one service. This is particularly relevant if you're doing canary testing or A/B testing. Let's see how we can accomplish something like that. So we are in this directory here. Go to manifest, standalone, open up greeting istio.yaml, and we go very much to the bottom here. On line 46, we have 50 weight assigned to greeting hello. And on line 52, we have 50 weight assigned to greeting howdy. Let's change that weight, where we make this 90 and make this 10. So now when we invoke the service, 90% of the traffic, about 90% of the traffic should go to greeting hello, and about 10% of the traffic should go to greeting howdy. Let's save it and get out of it. Apply those changes now. As you can see, our virtual service definition has been updated. So now the next step for us is to go ahead and invoke the service again. We're going to use the same command that we did earlier. And just to get a better sample, instead of 10 times, we will invoke this 50 times. We change the number to 50 here and hit enter. As you can see, most of the responses have been hello, 1 howdy. Now, again, this is expected over a large sample. So if you're saying we invoked 50 times, so about 5 times should have been howdy. But again, this is a small sample. So let's try to run this command once again. And if you go here now, 1, 2, 3, 4, 5, 6, 7. So about 10%. Let's try to run this once again. One, 2, 3, 4, 5. And this is exactly 10%. So the idea being that over a large sample, if you do multiple times, about 10% of the traffic will go to one service and about 90% of the traffic will go to another service. Now, you can start setting up health checks. You can start setting up monitoring alarms and see as you are doing canary and A/B testing of your Java applications in the Kubernetes cluster, how you can automatically apply a new virtual service definition based upon those health checks. And that's what makes Istio that much more interesting. Quite often, when your services are deployed in the Kubernetes cluster, you need some visibility into them. There are plenty of tools available, such as Prometheus, Grafana, and many others that provide you visibility into how your microservices are running, how are they connected. Kiali is a new tool that has been introduced recently as part of Istio. Well, first of all, going with our sailing theme around Kubernetes, Kiali is yet another Greek word meaning monocular or spyglass. Kiali project provides answers to the questions: what microservices are part of my Istio service mesh and how are they connected? You can get answers such as gain insight into how your mesh is functioning, have a checkup with your mesh's health. You can choose what kind of graph to display. You can zoom in to see what is happening with a single component. You can visualize your traffic flow, browse your service mesh by applications, workloads, and services, and much more. Now, by default, Kiali is disabled when Istio 105 is installed, and so it needs to be enabled. So let's get started with that. We are in the Istio directory. This is how we install Istio. So let's go ahead and enable Kiali for us. So I will say helm template, and I'm going to set the value of kiali.enable to true. And where am I setting this value? I'm setting this value in install Kubernetes helm Istio. And of course, we need to provide the name of the app, which is Istio in our case, and the namespace, which is Istio system. And then we're going to get the new template generated for us in home/istio.yaml. So this generates a new template for us with only Kiali being enabled. And now we can conveniently apply this template. This will configure our Istio with only Kiali being enabled. You'll see a lot of warning messages here, so don't be confused by them. Those are only warning messages because it's trying to give you a warning on what kubectl command should be used. But kubectl apply is the right command that we have done over here. Now, let's look at whether our Kiali pod has been successfully started. So we'll say kubectl get pods. We want to see the pods in the Istio system, and we only want to see the pods that have the label app Kiali. And there you go. So our Kiali pod is now successfully up and running. So the next thing we need to do is now open our Kiali dashboard. So for that, we will say kubectl -n Istio system, because that's our namespace. Then we will do a port forward in this case. And when we do a port forward, then we need to get our Kiali pod. So we will say kubectl once again in the Istio system namespace. Continue the command. And I'm saying get pod. And I'm saying give me the label Kiali. Continue the command. And I'm saying here is my JSON path. And my JSON path really looks like, give me all the items. Actually, the first one, get the metadata, get the name, close the JSON path, close the command, and then close the command once again. And here I'm saying, give me 20,001 port on the host, where 20,001 is on the container as well. So let's go ahead and run this here. So now what we have done is we have done the port forwarding of the Kiali port here. Okay. Let's open up a browser tab and look at our Kiali dashboard. And we said it is forwarded on port 20,001. So let's get that. The default username and password is admin. So username admin, password admin, and login. And this is your default Kiali dashboard view. It shows you the application here. So there's one application. This is the Istio system itself. This is in default namespace. So let's click on this application here. You get more details about the application. Well, of course, we deployed only one application, and that's what it shows here. So let's click on greeting. It shows it's got two workloads, greeting hello and greeting howdy. And this is my service. It's looking healthy right now. You just hover over it, and it kind of gives you a basic health metrics based upon Envoy. I can dig further into it. I can say greeting hello, And then it starts giving me more details about the particular deployment itself. And then it shows me the services it is connected to. I can go to applications here. Again, get the same view. I can go to graph here. Now it's showing me the versioned app. That means the current version of the app that is being deployed. I can change this to workload. And now I'm seeing greeting hello and greeting howdy. So those are my two workloads essentially that are being displayed over here. So we're going to go back to a terminal, invoke the command to access the application again, and see how this changes. So let's go ahead and open a new tab of terminal here. I'll go back to browser for a second. We will copy the command to invoke the application again. And because we are in a new terminal, we need to export the ingress host and port once again. So let's export them. So this sets the value for my ingress host and port. Back in the browser, let's say we want to invoke it 10 times. So copy it and paste it here and let it go. We get the response back. This is still about 90-10 split. Now if I go back to my browser, look at the Kiali console, I can change this to every 5 seconds and say refresh it now. And right away you see that Istio ingress is now invoking greeting hello and greeting howdy. And greeting hello particularly is all green because that's the service it invoked. And here you can see the HTTP traffic chart as well. Now I can go back here, invoke the service, and this time, let's say we want to invoke it 50 times so that at least sometimes howdy is invoked as well. Okay, we saw howdy invoked a few times. And you can see automatically the graph refreshed. So you can get a good feeling of, how your overall service is looking, how healthy it is, and what values does it carry. Now, there are a lot more things here that you can explore. So if you have multiple applications deployed, they will of course be displayed over here. You can filter by namespace. You can get all kind of graphs here, as we saw. So by app, by service, by versioned app. You can of course get more details about the service itself. So if I click on say greeting service here, it gives me more details about the service. It shows me the associated Istio resources that were created. So what are my source workloads? Well, it's an ingress gateway. And then what is my associated virtual service or my destination rules? So I can start getting a lot more details from the Kiali console itself. So I would recommend give it a shot. Now this is a new release. This is the first time it has been integrated into Istio 1.0.5. The way the integration may look like in Istio 1.1 may be different, but definitely worth keeping an eye on. Now let's make sure we also clean our port forwarding. So we're going to hit Control C here, and that way the port is not occupied and our connection is clean. To do a final cleanup of Istio, let's remove the Istio greeting resources. That can be done by kubectl delete -f, and we need to go into our workspace directory, manifest standalone greeting istio.yaml. This is going to delete our gateway, destination rule, and virtual service. And finally, we can also delete Istio altogether from the cluster itself. Helm delete Istio and purge. It says release Istio is deleted. Oftentimes we have seen certain CRDs that are created by Istio are left over, and so we may have to delete them explicitly. So in which case you go kubectl delete -f, install kubernates helm Istio templates CRDs, and they are in the Istio system namespace. And that leads to a clean deletion of Istio from your EKS cluster. Of course, we can delete our app as well. So if we look at Helm ls, our app exists. Okay, so let's go ahead, Helm delete my app and purge. That deletes our app as well. Going through the entire process of building your application, creating a Docker image, updating Kubernetes manifest reapplying those manifests to Kubernetes cluster could be daunting when you want to focus mostly on building your application. This is exactly where deployment pipelines help. This chapter will show two types of deployment pipelines. One that you can run during your local dev setup, and another that can run reliably in the cloud. The first option that we will consider is Scaffold. Scaffold is an open source command line tool that facilitates continuous development for Kubernetes applications. Scaffold provides an opinionated, minimal pipeline to keep things simple. You can iterate on your application source code locally, then deploy to a local or remote Kubernetes clusters. Scaffold detects changes in your source code and handles the pipeline to build, push, and deploy your application automatically with policy-based image tagging and highly optimized, fast local workflows. It also provides building blocks and describes customizations for a CI/CD pipeline. Use Scaffold run command end-to-end or just part of Scaffold stages from build to deployment in your CI/CD system. Scaffold does not require maintaining a cluster side component, so there is no overhead or maintenance burden to your cluster. A pluggable architecture is central to Scaffold's design, allowing you to use the tool you prefer in each stage. For example, Dockerfile and Jib can be used for building the image. Deployment can be done using kubectl and Helm, and Docker images may be kept on the local daemon or pushed to a registry. This could be useful for dev and prod scenario. On a local machine, you can configure Scaffold to build artifacts with local Docker daemon and deploy them to Docker desktop using kubectl. When the design is finalized, you can switch to the production profile and deploy with Helm to an Amazon EKS cluster. All details about Scaffold are available on this website. Let's take a look at the code now. First thing, we will take a look at kube configs that are available for us. At this point is pointing to the Amazon EKS cluster that we have created, but as we are building and deploying our applications with Scaffold, we want to point it to a local Kubernetes cluster. And as in this course, we have been using Docker for desktop, so we will point it back to that. Copy the context name and paste it here. Verify it. It is indeed switched correctly to Docker for desktop. Now let's see what applications are running here. Now, this is one of the applications that we have deployed into our Kubernetes cluster, and this was indeed deployed as an Helm application. So if you see Helm ls, it'll tell you actually that the application was deployed as Helm. So let's go ahead and delete this application for now, because when we are building with Scaffold, we essentially want Scaffold to build the image, prepare the Kubernetes manifest for us, and use that to deploy it to Kubernetes cluster. Okay, so let's go ahead. The application is now clean. The first thing we need to do now here is install Scaffold. Well, on this machine, I have already installed Scaffold, so your output may look a bit different if you're installing from scratch, but essentially you will have Scaffold in your CLI, and you can check the version or without -- version. So it says version 0.20.0, but if you give an incorrect command, as a matter of fact, it shows you the complete list of commands that are available to you. So it's always handy to see what's available to us. Now, app is our directory where all the application code is sitting. If we look at, say, scaffold.yaml here, okay. Now, this is a Kubernetes configuration file, and it says, I'm going to generate an image by the name arungupta/greeting. That's the image name that we've been using all along. And when I'm deploying to Kubernetes, then I'm going to use this particular manifest, which is greeting.yaml. Now, this greeting.yaml, if you remember, is a manifest that we used earlier, single manifest with two resources defined over there. And so that's lying around in our repo. So I'm going to copy it from standalone greeting.yaml and copy it to our current directory. Okay, let's open up greeting.yaml here. Now this, of course, has a deployment. And if I scroll forward, then I have service. Now, one other thing to notice on line 18 is we have image pull policy. It says always. Well, when I'm building with Scaffold, I don't really want to push the image and pull the image because that really adds up to my overall development cycle. So in this case, I will rely upon the default image pull policy. So delete that from here, save it, and get out of it. So now at this point of time, I think we're ready to start seeing the effect of scaffold essentially. Okay. So what I'm going to do is I'm going to bring a browser, split the screen, and then bring the browser here. Now, as you can see, our screen is split, and on the left side we have terminal, and on the right side we have the browser. So let's go ahead in the browser. We can say localhost colon 8080/hello. Well, this is where we expect our application to go live. It's not live yet because nothing has been deployed by Scaffold. So let's go ahead in our app directory. Let's run the command scaffold dev. This took the Docker file, build the Docker image, use the Kubernetes manifest, deploy that using kubectl to the cluster that is configured, and then deployed all the required artifacts for us. Now, if I go in the browser here, refresh the page, as you can see in the log, the app just got completed. So now if I refresh it, voila, we see hello. That is indeed the kind of response that we wanted to see here. So now think about your entire development cycle. You can easily have IntelliJ or NetBeans, whatever your favorite IDE, up and running. You keep making changes. As soon as you save it, Scaffold is now listening for those changes, and then it will right away build the image and deploy that using the manifest to your Kubernetes cluster. So enjoy your time debugging your applications and building your applications using Scaffold. Let's make sure we clean up Scaffold. So go to the terminal, Control C, and this will not only stop Scaffold, but it will also remove the deployment and the service that was deployed by Scaffold to Kubernetes cluster. When you're building an application where you don't need to be worried about the deployment pipeline infrastructure, then you need to think about a managed deployment pipeline. This is exactly where AWS Code Pipeline helps. AWS Code Pipeline is a fully managed continuous delivery service that helps you automate your release pipelines for fast and reliable application and infrastructure updates. Code Pipeline automates the build, test, and deploy phases of your release process every time there is a code change based on the release model you define. This enables you to rapidly and reliably deliver features and updates. Code Pipeline allows you to integrate third-party developer tools like GitHub or Jenkins into any stage of your release process with one click. You can use third-party tools for source control, build, test, or deployment. AWS Code Pipeline allows you to define your pipeline structure through a declarative JSON document, as we will see in our course, which allows you to specify your release workflow and its stages and actions. These documents enable you to update existing pipelines as well as provide starting templates for creating new pipelines. Let's look at the code next. Let's look at what our context is set at first. kubectl config get context is set to Docker for desktop, but in this case, because we are deploying to a Kubernetes cluster in Amazon EKS, we will switch our context to the EKS cluster. Copy the context name and paste it here. Okay. Now, as we talked about, code pipeline can be created using a JSON document. So this is the root of our repo. And if you look at it, there's a build spec.yaml right in the root of the repo itself. Now, in this, we are talking about version, first of all. This is version 0.2. It provides different phases. So install, pre-build, build, post-build, and there are multiple commands associated with it. So for example, in the install case, I'm installing the IAM Authenticator, kubectl CLI, setting the path, installing the right packages. In pre-build, I'm making sure that my manifests are appropriately prepared with the right image name. Then in the build phase, of course, I'm building the Docker image. And then finally, in the post-build stage is where I'm actually deploying to Kubernetes using my downloaded kubectl CLI. Okay, so let's go ahead and create our code pipeline. Now, in order to create the code pipeline, we will be using a module from EKS Workshop. EKS Workshop is a workshop built by Amazon, which allows you to get started with Amazon EKS and provides best practices around deploying your Kubernetes cluster in the cloud. So we're going to look at the module here. This is the module that we'll be looking at. This module provides extensive details. As you can see, the workshop itself has plenty of details about running your Kubernetes cluster in the cloud. But let's click here to go to the next part of the module. When you create an Amazon EKS cluster, the IAM entity user or role that creates the cluster is automatically granted system:master permission in the cluster's RBAC configuration. Now, in order to grant additional AWS users or roles the ability to interact with your cluster, you must edit the AWS auth config map. So let's create the IAM role first, and then we'll edit the auth map. So let's go down here, click on this button. This will copy the command for you. Now, in our case, we don't need CD environment. This is specific to the workshop. So we will just copy this command. Copy it here, and in the terminal, paste the command. And all the commands are executed for us. It generates a Kubernetes role. Back in my browser. Now let's copy the command for modifying my AWS auth config map. And this command can be literally copied as it is. Now the important part here is we are patching the auth map for a particular Kubernetes cluster. So it's important that your kubectl config is set correctly. So paste it here. And this is looking good. Now the next step here. The workspace uses a sample Go repo, so we don't need to worry about that because this is a Kubernetes for Java developers course. And in this case, we will be using our own repo, the simple greeting application that we have been building. So let's skip this part of the module. Now we need to generate a GitHub access token. This will allow code pipeline to receive callbacks from GitHub. So click on this page here. You go to personal access token, and we are going to call this as Kubernetes course. Give it full access for the repos. Scroll down, click generate token. Now this shows our generated GitHub token is blurred out for a reason, but let's copy it here, and then we can move to the next step. Click here, and now we are ready to launch a CloudFormation template. This will generate our code pipeline. This will generate our code build and all the services that are required for it. So let's click on it here. Make sure this is in the right region, US West 2. This is exactly where our Kubernetes cluster has been created as well. Keep the stack name as it is. We need a GitHub token. Actually, we need a GitHub user first. Call that as my GitHub user. And the GitHub token we already copied from the previous screen. Paste it here. Our GitHub repo is LIL Kubernetes for Java. Branch is okay. Everything else looks good. And our EKS cluster, of course, is Kubernetes course. Click on accept here because it's going to create IAM resources, because it's going to create AWS resources using that IAM role, and click on create stack. And now it's going to show you the progress as the different resources are being created. You can click on refresh button here to see the progress status. After waiting for about a minute or so, you can see that the create is complete for the EKS WS code pipeline. So now what we can do is we can go to the code pipeline service from our services panel here. And we can see there is a code pipeline that is automatically created for us, and it says just now. So click on the code pipeline, and it shows you a graphical display of different stages, source and build. Source just succeeded. That means it was able to check out the entire source. And for the build, we can track the progress here by clicking on details. It shows complete progress here. And if I go down, I can say, tail the logs for me. The most important part here to understand is all of this build infrastructure is highly scalable and running for you in the cloud, where you can continue to focus on what your application needs to do. The whole process could take a few minutes, but if you wait for some time, then eventually you will see that the upload artifacts is success and is true. What that means is eventually we've been able to apply kubectl apply manifest standalone greeting pipeline.yaml. This is sort of where our single manifest with two resources, one deployment, one service are defined. And that's the manifest that is using to deploy the artifacts to the Kubernetes cluster. So now if I go to the Kubernetes cluster and look at what services and deployments are existing. And as expected, our service, our deployment, and our pod are existing, and the pod is one of one. So that's really good. Now, it also has an external IP, external load balancer, because the service type was load balancer. So essentially, AWS created an ELB or an elastic load balancer for you and exposed the service on that. And the port is, of course, 8080. So let's try to access this service now. Let's copy this command here, and we're going to paste it here. Now, sometimes it could take 2 to 3 minutes for an ELB to be provisioned, so let's try it and see what it gives us. Hello, that's exactly the output that we expected. So now we just saw our Java application packaged as a Docker container, deployed as a Kubernetes deployment, accessed using a Kubernetes service, deployed using code pipeline, fully managed in the cloud. Thanks for watching this course. If you want to learn more, here are some links for you to refer to. Amazon Corrado is a no-cost, multi-platform, long-term supported downstream distribution of OpenJDK by Amazon. You can use it on desktop, on-prem, and in the cloud. It is also available as a Docker image and very convenient to get started with. Docker.io is your primary resource on how to package your applications as Docker image and run them as containers. Kubernetes releases are available every 3 to 4 months, and new features are constantly getting added, and API versions of the resources keep getting updated. It is always recommended to refer to kubernetes.io for the definitive docs. Learn everything about Istio Service Mesh on istio.io. Another area to watch in Service Mesh space is AWS App Mesh. This is a managed service mesh recently introduced by Amazon. More than 50% of Kubernetes runs on AWS Cloud. Amazon EKS is Amazon's managed Kubernetes service. You can find everything about it at aws.amazon.eks. If you want to learn more about how to use EKS more effectively, then eksworkshop.com is a self-paced hands-on workshop that'll get you started. I hope you really enjoyed the course. I also hope this course gets you ready to take your Java skills and apply them to Kubernetes with ease.